Okay, so yeah, we'll continue with entropy today. So last class, and many of the last previous classes, we encountered a state function called entropy from our discussion of heat engines and thermodynamic cycles in a very simple cycle, an idealized cycle, the Carnot cycle. And through a lot of discussion, we saw that a very mechanical and practical way to compute entropy changes is this expression for the differential entropy ds is equal to dq reversible over t. And you can think of this as 1 over t times dq reversible, okay, if you want, and if that helps you. Because in all of the cases that we encounter where you have to compute delta S through this, through the use of this differential form, it boils down to finding what dq reversible is, okay? And dq reversible is determined through analysis of the, through application of the first law. So that was the, one of the things I hope you got out from our discussion of the Joule-free expansion that we did on Friday, which I show here in this diagram again. And I'll just recap that discussion very quickly. And in that experiment, the question was, we have a gas that's isolated in one part of a container. We remove the partition. And then at the moment we remove the partition, the system becomes an isolated system. And that gas, which we take to be ideal, expands to fill in the vacuum space of the container, which is rigid and well insulated. Hence, the system is isolated. And the question was, what is the entropy change of that process? In order to do that, we had to construct a reversible path because we all agreed that the process initially as posed, this expansion of gas into vacuum, was an irreversible process because we would never see the reverse, whether we waited forever and ever and ever. And so it was irreversible. So we knew that delta S could not be 0 for this isolated system. So in an isolated system, delta S can be greater than 0, equal to 0. And of course, it can't be less than 0. And so as a side note, let me finish this. So we had to construct a reversible path that would connect the two equilibrium states, the two equilibrium states being the gas on one side of the partition and then the gas fully distributed at equilibrium over the entire volume of the container, okay? And so we had to construct a reversible path. And a reversible path that we constructed was an isothermal compression, where we compressed the gas back to the initial state. Okay, and we can do this by adding a piston or a cylinder. So what we can do is, for instance, here in the bottom graph, we have our gas expanded. We can hook this up to a, let me see if I have another, I don't have another picture. But what we can do is hook this bottom system now to a thermostat to keep the temperature constant. And then we can have a piston, for instance, that we use. And we would push that piston in order to compress the gas. And of course, there would be work in this system. But of course, since it's ideal gas and it's isothermal, we know that delta U would be 0. So the work then would equal the heat interaction in this case, okay? And another side note, we know then that the entropy of an isolated system increases if for all irreversible processes. And we know that there's nothing ideal in the world. And so, you know, a very deep thing one can think about is because of thermodynamics, which is so pervasive in all of science, it is really I would say, a pillar of modern science. In fact, you can also think about taking this idea or concept of entropy increase in a isolated system and saying that the only plausible conclusion one could perhaps conceive that is consistent with the laws of thermodynamics, in particular the second law, is the Big Bang. And cosmologists have argued that the Big Bang really is a state of 0 entropy. And this is where the origin of our universe, in the current understanding of cosmology today. So at the moment of the Big Bang, entropy was zero, and ever since then, entropy has been increasing and will continue to increase. Now, that's almost a naive and superficial statement, but in fact, I wanted to say that because it goes to the point that uh, entropy is so fundamental. It explains that, and in fact, very recently, if any of you know Stephen Hawking and other physicists, they were debating what happens with black holes, and the argument they had to invoke was that of the second law in entropy and information. So entropy is one of these things at a very deep and nuanced level. It's not just something to torture students, but in fact, it pervades every aspect of modern science. And next semester, if you have my section of thermal, I will discuss briefly, due to lack of time, how Planck, in fact, used thermodynamics. It was an analysis of thermodynamics, and in fact, entropy that allowed him to sort of construct a model where energy was quantized. He did not set out and say, well, I'm going to quantize energy. In fact, what he started out with was the second law of thermodynamics in the form as posed by Boltzmann, which we will discuss today. Okay? And that's what led him, and he didn't know it at the time what he was doing. All he said is that the natural consequence of entropy increase has to be that there is something about energy that is quantized. So this is something that is overlooked by many who purport to understand thermodynamics and entropy, but this is what happened historically, and you can't distort history. So we will discuss that if you have my section next semester. And it's a very complicated thing that he was trying to do. You have to understand quantum mechanics very deeply to understand what he did, but the overall point was that he had to invoke the increase of entropy. And that is what led to the birth of the idea of quanta, though people will not discuss this. Okay, so let's go back to this idea of the Joule-free expansion, and we went through the whole discussion of that. I'm not going to reiterate everything. As I told you, the whole point was what is delta S for that forward process, which is irreversible. And the point here is that we needed to get dq reversible right here, as I mentioned earlier in the class, right? And you can think of this, for those of you, is just it's just dq reversible, okay, times this 1 over t. And so it boils down to getting an expression for dq reversible, and that dq reversible expression always will be determined through a first law analysis. Okay, so put that down in your notes, right? It's sort of a useful bit of approach to problems if you have to use this expression. The first law, in this case, again, as I mentioned, in the ideal gas case, because we have a reversible process from 2 to 1, which is isothermal, du is 0. And so that gives us a very easy expression for dq reversible in terms of work. And we know what work is. That's very simple. And so we can go through this analysis. Now this should be all straightforward from our first part of the course on the first law. So I'm not going to spend any more time on it, and go to the punchline, which was that delta S for the process 1 to 2, which we all agreed is irreversible in the isolated system, turned out to be nr times the log of the ratio of the volumes. And if we take the second volume, the full volume, to be twice the initial volume, it turns out to be nr log 2. But the important point to keep in mind is that delta S, okay, scales as the ratio of the volumes. And this is very important, okay? So larger volumes correspond to larger entropy, okay? And there's a very deep idea here behind volume, and it's related to something called phase space. And if maybe you heard of this in your classical physics courses or not, but volume is just a representation of the phase space that's available to a physical system. Okay, so this is what is really going on here. And this is something that one would encounter in a graduate level course in statistical mechanics or statistical thermodynamics. But anyway, for this course, we know, or we can see that this entropy change really is directly related to volume. There's nothing related here to chaos or to disorder. right? This is something else I wish to impress upon every one of you, is that for this process, though you may have heard people say, well, okay, the gas expands because it increases disorder or chaos. Well, the expression is the only thing that one trusts. And in this case, the expression only tells me that delta S is related to a change in volume. Okay, nothing else. I cannot conclude, or I cannot believe anything else, whether it makes me feel good or not. The expression is the expression, and that's what it is. Okay, so delta S then really in this case depends on the available volume to the gas. And in a deeper level, this is called phase space, okay, to the particles of the gas. And if we have V2 equal to twice V1, this ratio just becomes 2, and we see that delta S is nR log 2. Okay, so for this isolated system, we saw that the entropy does increase. It's greater than 0 because log 2 is greater than 0. N is the number of moles, R is R, the universal gas constant. Everything is positive, and so delta S is greater than 0, as one would expect. Okay, so that's great and all. Now what I want to do is look at the same experiment, but from the point of view of particles. Okay, and this really will help us understand what entropy is at a very fundamental level in the case of an isolated system. And at this point, I haven't said anything about open systems. Okay, so keep reminding yourself as you go through the notes up to now, is that we've been talking about isolated system. Okay, an isolated system, and it's very important to keep that in mind. So now let's look at the Joule-free expansion again, but this time with particles, okay? Because now, as opposed to Carnot and Joule and Maxwell and those engineers, we know that there's particles involved. So now we have a particle view. And since we're still dealing with an ideal gas, we'll just call these things point particles, okay? And the way we're going to do this is construct the experiment in this manner. So our initial state to model, and if there are any questions along the way, please just chime in. So our initial state, what we're going to do is say, well, we have a container, okay? And we're going to make this what we call a lattice model. Okay, and lattice models are very useful in physics. Okay, and statistical mechanics and approaches of this nature to understand entropy at a very fundamental level. And the lattice model is that we have lattice sites where we can put our particles. Okay, so this can be three-dimensional. I will just pose it in this 2D case because that's all I have to draw, and it's easier to see. So when we had our gas on one side, let's say, we can take this container that I've just drawn here as this rectangular box to be that one side of the gas of the container. So the initial state, remember, was where we have a partition and all of our gas is on the left-hand side. Okay, and so what this represents, this black box, is the left-hand side. Okay, and so what we're going to do is we're just going to make discrete little sites. Okay. Let's say we have discrete sites, okay? And what we can do is we can put a particle here in this site. We can put a particle here in this site. We might have another particle here in this site. We might have a particle here in this site, okay? So that's what we're going to do. So this represents the left-hand side initial state, okay? And we'll say that we have capital N is equal to the number of total sites. Okay, and little, we'll call little, we'll say M. M is equal to the number of particles. So these are the gas particles that we have. Okay, and we will stipulate that N, capital N, is much, much, much greater than little m. Okay, and we have to do this because we want to approximate this. This allows us to approximate ideal gas conditions. Because in an ideal gas, the particles are far enough apart that we say that they don't interact. So in our lattice model, what we say is that we have a whole bunch of sites, N, capital N, but there's so many of them that we can put all of our little m particles, the m number of particles, and they're sufficiently spread out on this lattice that they don't see one another in any realistic sense that we would like to envision. Okay? And so this is a way to approximate an ideal gas. Okay, so we have this very important constraint that n is much, much greater than m. And we also will take something such that, let's see, we'll do it the other way. We have another constraint that m over n in this limit is constant. So even though n is much, much greater than m, we'll say that m over n is constant. And what we're going to do is say m goes to infinity, some very large number, and n goes to infinity, which is some very large number, because we're dealing with on the order of 10 to the 23rd particles, okay? So little m, the number of particles, is usually, because we're dealing with moles, on the order of 10 to the 23rd, right? It could be more. So it's a huge number, okay? And if n, capital N, is much, much greater than little m, then we're talking about sizes that we can effectively say, for mathematical purposes, go to infinity. They're very large. Okay, so this is a mathematical constraint that we use, and with those constraints, we still allow m over n to be constant. So the ratio of m over n, even though they're tending towards very, very large numbers, this ratio m over n is constant. And what this mimics is a density. Okay, so we have to make sure that we allow for that constancy of m over n, because that's the density of the system. Okay, and so that's fine. This is all totally fine and self-consistent. Okay, so capital N, much, much greater than little m. M and n go towards infinity. Of course, this is, again, realistic. And the ratio m over n is constant in order to represent a constant density. Okay, so we can let both of those guys go to large numbers. It's okay. Okay. The thing is that even though they go to large numbers, that ratio is a constant. That's totally fine. Okay, so that's the setup of the system. Okay, it's a lattice model. It's a lattice model. So our final state, okay, our final state, then, both at equilibrium, is when we have, let's see, we have this. So now we have no partition and the gas is all over. Okay, so we still have the same number of particles. Little m hasn't changed, okay, and the temperature hasn't changed. Okay, we just have more volume. And so the way we'll do that is, of course, we have a bigger box now. Okay, and I'm going to say that, I'm not going to, you can imagine that it's a bigger box, and, but what I'm going to say now is that in the final state, we have now 2n sites. So what I've done is effectively double the volume. Okay, I have the same number of particles. So 2n is equal to the number of sites. Okay, m still represents the number of particles. That hasn't changed. Okay, and the same thing applies, n much, much greater than m. M goes to infinity, n goes to infinity, but m over n is a constant. Okay, so those are the same things. Okay, so the only difference is now we have more sites. Okay, so we can put our particles here, same number of particles, okay, etc., and you can fill them in. Right, so here are the two states. Our initial is up here where we have n, and then the final is where we have 2n sites. Okay. All right, so the question we want to ask now, okay, is something that I'm not going to motivate, but I'm just going to ask. And the question here is, we have n sites and we have m particles. Okay. How many ways can we put in m number of particles into n sites? Okay. And I'm going to now stipulate that these are indistinguishable. So you can't tell one particle from another. Okay, they're indistinguishable. So they're not labeled. So you can't tell this particle from this particle. Okay, they're all the same. Okay, and the question is, how many ways can you put these little m particles into capital N sites or capital 2N sites? And it turns out to be, this is something combinatorial, and we call that W. So W for the first state, our equilibrium state 1. So this is the number of ways you can put in little m particles into big N sites. Okay, and I'm just going to tell you what that is. It's n factorial over m factorial n minus m factorial. Okay, it's just a combinatorial equation. I won't prove it. I don't have time, and at the moment we don't need to see the proof. Okay, and this is for indistinguishable particles. For the state 2, we have the same thing, but now we have 2n sites. So this is going to be 2n factorial. We still have m particles, so there's going to be an m factorial on the bottom. And we'll have 2n minus little m factorial on the bottom. Okay, so these are the ways we can put in little m particles in the number of sites that we have in the initial and in the final states. And both of these are equilibrium states. These are rather large, okay, because both n and m are going towards infinity. So we might, we might think that W1 and W2 are quite large, and they are quite large. Okay, you can just think about this. There's a lot of ways, even if you had just like 10 particles in 100 sites, there's a lot of ways you can put them in there. Okay. So in order to deal with numbers that are tractable, okay, what we're going to do is just deal with the logs of these. And there's another way. There's one point. One point is to just deal with tractable numbers. We don't have to deal with like 10 to the 23rds and this and that. We can just use 23 if we take perhaps a log of something, and that's exactly what we do here. We can deal with the logs of these numbers. So we can consider the log of W1 and the log of W2, natural log. We can use log base 10, we just use natural log. Okay. So if we were to take the log of both of these sides, we would have the log, in this case, of n factorial over little m factorial n minus m factorial. And on this side, we would have 2n quantity factorial. Whoops. Right, I forgot a log. Is equal to natural log of 2n factorial over m factorial 2n minus m factorial. Okay. So we're going to consider the logs just so we can deal with normal numbers. Okay. And in fact, dealing with logs is actually good. In this case, let's just kind of decompose what this log is. We have a log of a ratio, and I hope everyone remembers that this can just be written as log of n factorial minus the log of m factorial minus the log of n minus m factorial. Okay, that's what log of W1 is. Okay, that's really because you have this ratio of in the log, in the argument of the log. What happens then is it just becomes the addition of log terms. Okay? And you can do the same for log of W2. Right, that's just going to be the log of 2n factorial minus the log of m factorial again, minus the log of 2n minus m factorial. Okay, anyone have any problems with those two expressions, A and B? Okay, it's great. So recall, m goes to infinity, n goes to infinity, but m over n is a constant, just to recall, right? There's a nice approximation, it's called Stirling's approximation. And that's what we're going to use because it applies for logs. So as n goes to infinity, natural log of n factorial can be approximated as n log n minus n, where n can be anything. Okay, maybe I can, so this is just a general mathematical result. And I won't prove it. Okay, this is general. It can apply to anything. So maybe I should put here another as q goes to infinity, natural log of q factorial is q natural log q minus q. So this is q times the natural log of q minus q. Okay, and q is any variable. So this is a general mathematical result. And because we stipulated these guys, and this is applicable, we can now use that result to compute A and B. Okay, we can use that result to compute A and B. Okay. So let's do that. Okay, so let's start with log of W1. So I'll make these blue. Okay. So log of W1, which is this guy right here. Okay. Okay. So you can we'll just do that. So the first term is n log n minus n. So it's n log n minus n. Okay, that's this term. Then we have this term, which is just going to be little m. And it's a negative. Right? So there's a negative sign there. So we have to have this times m natural log m minus m. And if I make a mistake, let me know. So that takes care of this term. And then we have a minus term that corresponds to this. So that's going to be minus n minus m natural log n minus m minus n minus m. Okay, so this is q natural log q minus q, if you need to remember that. Okay, but q now is n minus m. And we have to make sure we have this minus sign for the whole thing. Okay, so a natural log W1 is equal to n natural log n minus m natural log little m. The minus minus gives me a plus m. Okay. And then in the last term, I have minus n minus m natural log n minus m. That's the first term. And then I'll have a minus minus, so that'll give me plus n. And then I have a minus, 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 minus m, I believe. Okay, so we can do some reduction here. So natural log of W1 is equal to, let's see, we have an n natural log n. Here we have a minus n and a plus n, so they cancel. Here we have a plus m, and here we have a minus m. So those two will cancel, so we don't have to worry about those. So we have m natural log m left. So we've taken care of this term, and then we have one final term left, which is minus n minus m times the log of n minus m. Okay, any questions or comments? And then what we can do, just to refine this, is just write this as n log n minus m natural log of little m minus, and we'll just break this term up. So we have n natural log of n minus m, okay, and then plus little m natural log of n minus m. So that gives us the natural log of W1. It reduces down to these very simple things. Okay, any questions or comments? Now we can do the same for W2. So let's write W2 down. W2, remember, was 2n factorial divided by m factorial times 2n minus m factorial. Okay. And so the log of W2 is equal to log of 2n factorial minus log of m factorial minus the log of 2n minus m factorial. And now we just apply Stirling's formula or approximation. Apply Stirling's approximation. Okay. So log of W2 is equal to log of 2n quantity factorial. That's just going to be 2n natural log of 2n minus 2n. Okay. And then what else? Okay, so then we're going to have the minus log of m factorial. So that's going to be minus m natural log m minus m. Okay, so we have this term done. We have this term done. And then finally, we have to do the last term. Okay, and that last term, again, it's going to be negative. Then we have a bracket here. So log of 2n minus m factorial is just going to be 2n minus m natural log of 2n minus m minus 2n minus m. There we go. So now it's just a matter of simplifying everything. So we have here, what I'm going to do is, since we have a log of 2n here, okay, I'm just going to say that this is going to be 2n log of 2 plus 2n natural log of n. Okay, I can do that. Okay, I just broke up that log. So we have 2n times the log of 2 plus 2n times the log of n minus 2n. So I've taken care of this term. I've taken care of this term. Now I'm going to look at the first bracket. So that's going to be minus m natural log m plus m. So that takes care of that bracket. And then what we're going to have is the last bracket. Okay. And that is going to have a term which is minus 2n minus m natural log of 2n minus m. So that's that first part. And then that last part is going to be a plus 2n minus m, plus 2n minus m. All right, I think that's about right. And now we can simplify this expression. So natural log of W2 is equal to 2n natural log 2 plus 2n natural log capital N. Let's see, we have a minus 2n here and a plus 2n, so those cancel. I've taken care of this term. I've taken care of this term. I have a plus m here and a minus m here, so those two terms cancel. So then I'm left with a minus m natural log m, which is this term. Okay, and then I have this term in brackets, which I'm going to, again, decompose as minus 2n natural log of 2n minus m. Okay, and then plus m times the natural log of 2n minus m. Okay, so that takes care of this guy. Yeah, that makes sense. Any questions? So we have log of omega, log of W1 and log of W2 now. This is log of W2. And we have log of W1 right here. Okay. And remember, W1 and W2 represent the number of ways you can put little m particles in the sites that are representative of those two equilibrium states. Okay, so if you didn't follow my derivations to get to the logs, don't worry, the video will be posted and you can go through that on your own. Okay, I just wanted to show you that we would get to these things. And now what we're going to do is take the difference of the two logs. So what we're going to do is say, let's take the difference log of W2 minus log of W1. Okay, so now log of W2 minus log W1. Let's take that difference. Okay, so let's see if we can do this without having to sort of go back. Maybe we won't be able to. So log of W2, let me just write it down. Okay, so here's log of W2 right here. Okay, so log of W2 minus log of W1. So that's the log of the final state, W, minus the log of the initial state, W. And let's see what that gives us. Okay, there's going to be a lot of terms. So let's see. Log of W2 is right here. So let's just rewrite it. Okay, so that gives us 2n log 2 plus 2n log capital N minus m log of little m minus 2 times the capital N natural log of 2n minus m plus m times the natural log. Oh, let me just put this last part right here. Plus m natural log 2n minus m. Okay, so that's log of W2. Now we'll go and get log of W1 and then we'll put it in a minus. So log of W1, we'll make this color. So we're going to subtract it, so it's all here. Then we're going to have brackets for it. So log of W1 is up here. Let's start with, it's right here. Okay. So the first term is n log n, and the second term is minus m log m. So let's just put those in. Those are the easy ones. N log n minus m log m. Okay, so those are the first two terms for log of W1 right here, 1 and 2. And then we have this minus capital N log of the difference. So we'll put that in, minus n times the log of n minus m. So that takes care of this term. And then finally, we have little m times the log of that difference. So we'll put in plus little m natural log of n minus m. And then we close the curly brackets. All right, so that's it. And now let's simplify and see what we get. Okay, let's see what we get. Let's see. All right. Let's see. So this guy, we have a minus m log m. And from the brackets in brown, we see that we have a plus m log m, which is this guy. Right? We have a minus sign outside of the brackets, and then this guy has a minus sign. So that's a plus. So those m log m terms cancel. That's great. We don't have to worry about them. Okay, what else? I wonder if there's anything else that cancels. Let's see here. Let's see. Anything, do people see anything that might cancel?
I see something.
Which one?
We have a plus 2 n log n, and we also have a minus 1 n log n. So those will subtract to just get us plus 1 n log n.
Okay, and where's that second n log n coming from?
It's near the end.
This guy?
Yeah.
And why did you say that? Because n is much, much greater than m? Is that because we can ignore the little m compared to the big M? Begin.
Actually, wait, no, not there. It's at the beginning of that second term.
Oh, okay, okay, gotcha. Okay, so you're here.
Yes, because at the beginning we have a +2
Okay,
n log n, and that will become a minus n log n.
okay. So let's go there. So what I'm going to do now, so I still have this, I'm gonna rewrite things. So we have 2n log 2, and you're saying that this first 2n log n is going to subtract this guy, and this guy. So that will leave us with n log n, if I'm not mistaken. Is that correct?
Yes.
Okay, good. All right. So that means we no longer have this term. We've taken care of this in part. This is gone, and this is gone. Okay. So I'm going to carry over the next two terms. So we have a 2n natural log 2n minus m, which is this guy, okay, plus m natural log of 2n minus m, which is this guy, right? We took care of this guy is gone. Now what we have is a plus n natural log of n minus m, and then a minus m natural log of n minus m. Okay, so that's what we're left with still. Okay, let's see here. What are we going to do? Well, now we're going to make this use of our approximation that n is much greater than m. Okay, so where we have these differences n minus m in the logs, okay, what this allows us to do is take log of n minus m and approximate it as log of n, and log of 2n minus m is approximatable as log of 2n, because we can ignore that little m compared to the terms that have capital N. Okay? So let's see what that allows us to do. So now we'll bring all of this stuff down. Okay. So can we make any changes here? Let's see. You have a 2n log 2 plus n log n minus 2n natural log of 2n. So that 2n natural log of 2n is this guy. Okay, where I said that since little m is much smaller than capital N, we don't have to worry about the little m. Okay. Now we go to this term and we'll do the same thing. This just becomes m natural log of 2n. Then that next to last term becomes n natural log minus m natural log n. Okay, so this term becomes n log n, and this term becomes minus m log capital N. Everyone okay? So that's this last equation that I wrote, and I hope everything comes out right. Let's see here. All right, so this is going to give us 2n log 2 plus n log n minus 2n log 2n plus m log 2 plus m log n. And there what I did is I said this is equal to m times log of 2 plus m times log of n. Okay. And then we have a plus n log n minus an m log n. All right, let's see what we have here. We have a plus m log n and a minus m log n, so these guys will cancel. Okay. We have, let's see here. Anything else?
Actually, wait, wouldn't you also be able to do the same thing you did there with the minus 2n log of 2n?
Okay, let's just hold, okay. If you want to do that, okay, let's, Sure, you want to do that? Okay. So that gives us 2n log 2 plus n log n. So this is going to be minus 2n log 2 minus 2n log n, okay, plus m log 2 plus n log n. Yeah, you're right. But wait a second, a lot of things cancel now. So let's see here. We have a 2n log 2 minus a 2n log 2. Okay. This guy's a 1n log n. Here's another n log n. So that's 2 times n log n. But wait a second, we have a minus 2n log n. So these guys will cancel. You follow? Everyone follow? What does that leave us with? Well, log of W2 minus log of W1 then is equal to, the only thing that's left is
MLN2.
okay, so I put examples here, or exclamation points, and I'm going to stop here. But wait a second. This log of W2 minus log of W1 is equal to m, which is the number of particles. That kind of be like moles, okay? It's kind of like moles. And number of particles is related to moles times log of 2. But wait a second. When we computed the entropy change for the irreversible process of the Joule-free expansion, we got something that was some number that represented moles times log of 2. And in this case, we said the final volume is twice the initial volume. So we got something, wow, look at that. So in this case, we didn't have to think about particles. All we said is something is expanding into, some continuum is expanding into some vacuum. And we got something that's some constant times log 2. And in this case now, where we looked at particles in this lattice model, and we compared this thing called the number of ways, W, and we said, well, what's W for the final state and minus the W of the initial state, and we take logs, but that's fine. Logs are representative of the W's. We get something that's a constant that represents the number of particles there times log of 2. That's really, really interesting, okay? And it's now very insightful about what entropy is, because what we computed above, which was this constant times log of 2, was delta S. So it seems that delta S is related to the W's. And now that we know what the W's are, we have a bit of an insight now as to what entropy is. Because each one of these then corresponds to S1 must be log of W1, and S2 must be log of W2. And this is now the insight that we're getting through this analysis using a lattice model of what entropy is all about, at least in terms of our discussion of an isolated system. Wow, this is a very insightful and profound lecture. So if you didn't follow the actual derivation, you can follow it on your own at a more leisure pace, since I upload these things. But what I want to impress upon you is that whether we come from a particle view or from a view that doesn't require any particles, the delta S for this process, okay, turns out to be very, very similar. And I'm going to finish this discussion to make everything equal. Okay, everything, it will be identically equal in the next lecture. Okay, but at this lecture, I wanted to show you log of 2 comes up again. All right, thanks for your attention. I will fill in the insight for what entropy is next class, if you don't already know. Any questions or comments? Okay, thanks everyone for contributing. And I will post the stuff, and I wish you a good week. Okay.